All right, thanks for tuning in. Today we are going to be talking about the active detumbling controller, Dot Detumble, which uses Earth's magnetic field to create a torque. My name is Tyler Clayton.
I'm Kate Doud.
I'm Levi Geller.
I'm Jaecks.
And I'm Brian Lopez.
All right, in this presentation, Cate is going to be giving a brief overview of Dot Detumble. Ren, as well as myself, are going to go over the control strategy. Cate is going to give a brief history. Ren is going to be looking over how it's used. Brian is then going to evaluate how useful it is actually. Levi is then going to determine how long it takes, as well as give it some applications of the control mechanism. And I will finally be giving some other interesting findings, while Cate will wrap everything up in a summary.
So the B-Dot controller is an active detumbling mechanism commonly used in very small satellites, utilizing only magnetorquers as actuators and magnometers as sensors. This detumbles the spacecraft by decreasing the angular moment of the spacecraft via Earth's magnetic field. Mechanically, this means magnetorquers are implemented, usually as three perpendicular electromagnetic coils. The magnetic field around the spacecraft interacts with the Earth's magnetic field, generating a torque to reduce angular momentum.
All right, so the way this works is as shown in figure 1, which shows the control strategy of the spacecraft for B-Dot Detumble in the spacecraft fixed reference frame with the Earth's magnetic field represented by the letter B and the vector notation arrow. Given the magnetorquer is aligned on the y-axis of the spacecraft fixed reference frame, when the spacecraft rotates such that the y-axis is in the same direction as the Earth's magnetic field, the temporal derivative of B as projected along the y-axis will be greater than 0. In other words, B dot will be greater than 0. Then the spacecraft will send a negative current through the magnetorquer coil so that the magnetic moment, or M, as shown in the diagram, is pointing in the negative y direction. When the spacecraft rotates such that the y-axis moves beyond B, making B dot less than 0, the current through the coil is reversed such that the sign of the generated torque is the same, resulting in a decreased angular velocity. As a side note, this method is similar to how an electric motor increases its angular velocity. Like the spacecraft example, it alternates current through a coil, generating an appropriate magnetic moment that creates a torque in the desired direction for angular acceleration.
All right, in this clip, we can see 3 reference frames. The black frame, which represents the satellite body fixed frame, the blue frame, which represents Earth's rotation, or the magnetic field rotation implemented using a tilted dipole model, and the purple frame, which represents an orbit frame. It is to be noted that the purple star is the satellite location in orbit. And as we've just discussed, the magnetic field is used by the satellite to damp out the angular velocities and thus detumble the spacecraft. This is known as B-Dot control since it depends on the changes in the geomagnetic field, which is denoted by B.
The B-Dot detumbling method has been used in a multitude of different small satellite missions. Ørsted is Denmark's first satellite, which launched from Vandenberg in California in 1999. It aimed to take highly accurate and sensitive measurements of the geomagnetic field. The BSAT is another example of a more current project. This is a CubeSat project of the Technical University of Berlin, and its goal was to verify microreaction wheels.
All right, so how is B-Dot Detumble used? To put it simply, B-Dot Detumble is used to bring the angular velocities of the spacecraft to 0 or near 0 after separation from launcher. As well as B-Dot law is also used to damp satellite motion when very high angular rates occur. This method is very efficient as it is accomplished using only electricity with no fuel expenditures and no resulting change in the velocity vector, which would alter the spacecraft's orbit. Once the angular velocities are brought to sufficiently low levels, the detumble is complete and the spacecraft begins the normal operations phase. As shown in the diagram, B-Dot tumble very simply is essentially the satellite reads the magnetometer data. It then updates the recent magnetic field history to a computer, and then it calculates the magnetic field temporal derivative, and then it sets the coil torque to the opposite sign of that derivative.
So how useful is it? Active magnetic control through the use of magnetorquers has several advantages over other actuators. Dot Detumble generally uses magnetorquers that use low power consumption and low mass when compared to control moment gyros as well as reaction wheels due to no need for extra actuators, which simplifies the overall design. Due to its simplicity, it has no moving elements and are therefore suitable for restricted volumes due to custom design possibility, which we can mainly see in CubeSats. There's a slow transient response due to the low torque production capacity, and it can exert external torques on the satellite body, which is needed to reduce angular momentum. During low Earth orbit, the magnetic field strength is enough to generate the necessary control torques. And finally, probably the biggest advantage of using a magnetorquer for Dot Detumble is that magnetic field modeling is still highly uncertain due to poor accuracy, which can lead to unstable control. Even the most accurate present-day computational models are only approaching reality, therefore making magnetorquers the most useful application to detumble.
So this diagram is showing how long the simulated spacecraft will take to detumble. So these lines coming down are showing the angular rate, the magnitude of that on the y-axis over the time in orbits. And it's very loud and a lot of information going on here, but that's because this is ran using a Monte Carlo simulation, which basically generated 50 random configurations of initial tumble states, as well as different gain values for the magnetorquer controller. And using that, the spacecrafts were simulated and to produce this graph right here. So this can be boiled down to basically these three lines, vertical lines, which show when each spacecraft detumbled. So there's three main areas. We have a minimum in green over here, and then a lot of average values in the center, as well as the maximum value at the top end. So what we can see from this graph is that in our best case scenario, it takes about half an orbit to detumble using this method. And at worst, we'll get 1.5 orbits to detumble. But usually, depending on picking the right gains, as well as getting an average initial tumble value or angular velocity, we'll have somewhere around 1 orbit to detumble. So what are some applications for this technology? This method of control does not work in interplanetary space because, as discussed before, we need a magnetic field for the magnetorquers to provide any torque to the spacecraft. And if there's no magnetic field, like if there is, like if we're in interplanetary space, then we won't be able to have any torque provided from this method. And on other planets, we can see this list right here, this table. We could use this on some other planets, depending on what sort of magnetic field they would have. Though not every planet would have a strong enough magnetic field for this strategy to be viable. Some current applications for the B-dot control method are that it's just kind of widely used on almost every satellite. It's the de facto standard for detumbling of very small satellites, according to one source. And because of this, it's really widely used in CubeSats, as well as big satellites, but especially the smaller ones, because it is relatively inexpensive, and it's very simple to make and fit into a small satellite. Some future applications, there's more CubeSat missions going up very frequently. This one, the ECE-3 is a satellite being developed by a French engineering school, as well as there's plenty of other CubeSat missions developed by colleges and other institutions around the world. So there are also improvements being done to the BDOT method. The study which produced that simulation that we went over in the last slide, that same paper actually also went over some improvements for the BDOT method, which can help make this already very widely used technology even better in future satellites.
Speaking of improvements to the BDOT method, a study conducted at the Space Research Center at the Polish Academy of Sciences looks into the optimization of control gain using the Dot Detumble algorithm. And as discussed, magnetic actuation is extremely useful for small satellite missions, which are becoming increasingly popular due to cost effectiveness and the rapid advancement of small satellite capabilities. That being said, pure magnetic control definitely has its downfalls, some of which include the fact that a small magnitude of Earth's magnetic field restricts control torques, and coils that are capable of generating torques lying in the plane perpendicular to the local Earth magnetic field vector can actually underactuate the system. So the study seeks to analytically optimize the control gain of the mechanism through the manipulation of applicable equations and simulations. Control gain in this context is essentially defined by faster decay of the satellite rotation rate, as well as lower energy expenditure. It is concluded that the optimal control gain occurs when omega c, which is the rate proportional to strength and control, is as close as possible to omega b, which is the rotation rate of the magnetic field. These findings can be seen in figure 10 and figure 11. However, this results in a very chaotic evolution and eventual convergence of psi, the satellite rotation rate vector. As one may expect, the study found that more control will result in higher energy consumption, while less control will result in lower energy consumption. As such, there's an opportunity cost between predictability and efficiency of the detumble mechanism and must be evaluated in the context of the satellite's mission.
Overall, the Dot Detumbler is a rather simple active stabilization method that only requires knowing the changes in the magnetic field as the satellite spins to reduce angular momentum. It is rather conservative in terms of computational power and only requires a magnetometer to indicate position and a magnetorquer as an actuator. As it requires a strong magnetic field to create torques, this method has been extensively used for decades in low Earth orbit and is very common in CubeSat missions. The optimization of our gain can be applied to future missions to make this method more effective in context in the future. Thank you guys for tuning into our presentation. Have a great rest of your guys' day.